Why do electromagnetic waves travel faster in air than in a cable? Why do some materials store electric energy better, while others respond strongly to magnetic fields? The answer lies in two fundamental material properties: permittivity and permeability. These parameters determine how electromagnetic fields behave inside matter. In the previous lesson, we learned that electromagnetic waves do not always travel at the same speed. While waves propagate at the speed of light in a vacuum, they slow down when traveling through real materials. This observation raises an important question. What property of a material causes this change? Engineers quickly discover that different materials interact with electromagnetic fields in different ways. Some materials allow electric fields to develop easily, while others strongly influence magnetic fields. These differences directly affect wave speed, energy storage, impedance, and signal propagation. To predict how electromagnetic waves behave in practical systems, engineers need parameters that describe a material's electrical and magnetic characteristics. These parameters are known as permittivity and permeability. Permittivity describes how easily a material supports the formation of an electric field. It determines how strongly the material responds when exposed to an electric field and how much electric energy can be stored within the material. Permeability describes how easily a material supports the formation of a magnetic field. It measures the material's response to magnetic fields and its ability to store magnetic energy. Together, permittivity and permeability determine many electromagnetic properties of a medium. They influence wave velocity, wavelength, impedance, energy storage, and field distribution. In many ways, these two parameters define how electromagnetic waves experience a material. Intuitively, permittivity can be thought of as a material's willingness to support electric field formation, while permeability represents its willingness to support magnetic field formation. Different materials offer different levels of support for these fields. Physically, consider a capacitor. The dielectric material placed between the plates affects the electric field and determines how much energy can be stored. A material with higher permittivity allows greater energy storage for the same physical structure. Similarly, magnetic materials with high permeability influence magnetic field distribution in transformers and inductors. Mathematically, the propagation speed of an electromagnetic wave depends on both permittivity and permeability. Increasing either parameter generally reduces wave velocity. This explains why signals travel more slowly in cables, substrates, and dielectric materials than in free space. Permittivity is one of the most important parameters in RF engineering. PCB substrates, transmission lines, antennas, and microwave circuits all depend heavily on dielectric properties. Engineers carefully select materials based on their permittivity to achieve desired electrical performance. For example, the characteristic impedance of transmission lines depends on the surrounding dielectric material. The electrical length of a PCB trace is also determined by propagation velocity, which is influenced by permittivity. Even antenna dimensions are affected because wavelength changes inside different media. Permeability becomes particularly important in magnetic components, such as inductors, transformers, ferrite devices, and electromagnetic shielding structures. Both parameters are fundamental to understanding RF system behavior and component design. Permittivity and permeability are the bridge between electromagnetic theory and real-world materials. They explain why identical signals behave differently in air, plastic, glass, ceramics, and other engineering materials. A common misconception is that electromagnetic waves behave the same everywhere. In reality, material properties strongly influence propagation speed, wavelength, field strength, impedance, and energy storage. Ignoring these effects can lead to significant errors in RF design. Now that we understand how materials affect electromagnetic waves, we can begin examining specific wave characteristics. In the next lesson, we will explore wave polarization and discover how the orientation of electric fields influences communication systems and antenna performance. In this lesson, we learned that permittivity and permeability describe how materials respond to electric and magnetic fields. We also saw how these properties influence wave velocity, energy storage, transmission lines, antennas, and RF system design. In the next lesson, we will explore wave polarization and discover why the orientation of electromagnetic fields plays a crucial role in wireless communication. If you found this useful, like the video, subscribe, and follow for the next lesson.